we're going to learn about acids and bases. So, I gave a description of what an acid was. There's 3 definitions of an acid. We're going to stick with the most strictest definition. And we're going to be a little imprecise too. So an acid has a hydrogen atom and some other base. So an acid is something that will donate. Acid is something that makes H plus ions. Note, H plus ions don't actually exist. Instead, they're actually H3O plus ions. And they're spelled hydronium ions. So an acid is something that makes hydronium ions. Technically, hydronium ions. This is the most strictest definition. And we'll stick with the simple case as is easiest. So an acid will turn into H plus and A negative. This A could be anything. Technically, under the new the more accurate definition, this would actually be HA will interact with water to make H3O plus and its conjugate base A negative. But this complicates things. It doesn't complicate it, but the formula gets longer because we have to keep track of water. So an acid, when it dissolves in water, dissociates into, make sure I get the spell right. Dissociates into ions. And there are 2 types of acids. There are strong acids, where it dissociates completely. This means completely turns into ions. And there are weak acids, where it only partially dissociates. Into ions. And bases are going to be the exact same.
Leave us out. Leave us out.
So what's the correct? They use A for acid, I think for B for base. And bases are going to be the same definition, except for it's going to be a B and OH. And it turns into B plus and OH negative ions. And everything is the exact same. It's just something that creates, so a base is something that disassociates, means turns into ions when dissolved in water, to produce hydroxide ions, OH negative ions. So a strong acid will look something like this. HA is going to 100% turn into some H plus, and wherever the A is, negative, the anion and cation. A weak acid looks more like this. This symbol right here means it can go back and forth. Can go both ways. Can go back and forth. So what's happening in a weak acid is we have together hydrogen and some anion, and it's going to break apart into H plus and A negative ion. So we have multiple molecules of the acid, and they're going to break apart into ions. However, some of the ions are going to come together and remake the acid. So when we look at any given time, we'll see inside of our solution. So let's say we have a weak acid. We will see inside of it water molecules. We will see in it H plus ions and A negative ions. But we'll also see HA, the acid molecule, as a whole. So weak acid, we actually have some of the molecules of acid that hasn't broken apart in ions. A strong acid, however, there is no HA, there's only H plus and A negative everywhere. It completely breaks apart, and there is water. Keep in mind, however, again, H plus doesn't exist. It's really H3O plus. It's technically H plus should really be H3O plus. But I like thinking in terms of H plus, as it just makes it easier. So the difference here is these whole molecules of acid. Note the word strong and weak doesn't mean how powerful the acid is. For example, hydrochloric acid. This is a weak acid by the definition I've given you. However, this is highly corrosive. You put it in, let me see some things we can wrap up. So if it comes into contact with glass, it will catch the glass on fire and start reacting with it. If you spill it on concrete floor, it will melt the concrete. You use a metal stirring rod, it will dissolve the metal stirring rod. If it comes in contact with water, it will quickly heat up. It will actually attack other acids, so it can destroy other acids. It's an oxidizer. It will react with oxidizers to explode. Anything combustible, any organics, any ceramics. The only thing you can store it in is some fluorocarbon plastic, some chemical that also contains fluorine. Because this fluorine is super, super reactive. But it's still a weak acid. The reason it's weak is because fluorine is very, very active and does not want to be by itself. Fluorine ion does not like to be by itself, so it will aggressively try to find something to attach to. And if it's in water with an H+, it will come over here and take it, so it can't disassociate completely. On the other hand, hydrochloric acid is a strong acid. When you put it into water, every molecule of HCl, and this is your stomach acid, turns into H+ and Cl negative ions. So to write the equation, HCl will turn into H+ and Cl negative. Or to do the more proper one, HCl with water will dissociate into H3O+ and Cl negative. And again, if you have an excess of water, obviously there will be water molecules left over. If you have more water than acid, then you'll end up with water still in there. Whereas HF goes back and forth between H+ and F negative. Or written more formally, HF with water goes back and forth between H3O+ and F negative. So we've been learning a lot about molarity. Molarity is the number of moles per 1 liter. This is a form of concentration. So if I write 0.1 molar NaOH, we have a special symbol for concentration. If I put brackets around this, you can think of it as an operator. This brackets right here means concentration of. So brackets mean concentration of. So this would be equal to 0.1 molar. So let's introduce pH. You probably heard this expression before. pH is how we measure how strong acid is. It is equal to the negative log, and this is base 10, of the concentration of H+ ions. And note, the real formula is the pH is equal to negative log of hydronium ions. But again, I'm going to be sticking with H+. let's suppose and let me look up, make sure, because this subject it can get very strange. pH of yeah. So let's suppose I have 0.2 molar solution of HCl. What would be the pH of the solution? So the pH is equal to the negative log of the concentration of H plus ions. So how many moles per liter? Well, again, let's say that we have a 100 milliliter solution, or let's make it easy. We have exactly 1 liter solution. It doesn't really matter what the volume is. You can always make up any volume. Volume is not going to make any difference. pH does not depend on volume. So HCl, when dissolved in water, will dissociate into H plus and Cl negative ions. So if I have 0.2 moles, or 0.2 moles per 1 liter, that's the molarity, then this is going to be a 1-to-1 ratio. I would have 0.2 moles of H plus and 0.2 moles of Cl negative. So in my solution, my concentration is 0.2 moles per 1 liter. So even though we usually deal with moles here, you can use molarity too. But my overall concentration is thus, I have a concentration of H plus also equal to 0.2 molarity. So to calculate the pH, we do negative log base 10 of 0.2. And we end up with the pH of hydrochloric acid, that is a 0.2 molar solution, has a pH equal to approximately 0.7 pH. And recall that we have a scale. The closer to 1 or we need to get 0 or less. The more to the left we are is acidic. 7 is neutral. And 14 is alkaline. Alkaline in this context means base. Basic for base. Usually they'll use alkaline instead of basic. I'm assuming the reason why they use alkaline instead of basic is because the word basic means basic. That's a word. It doesn't mean related to base. And kinda. They try to avoid using the word basic because it's confusing. If you say a chemical is very basic, what would you think that means? Usually if I tell you something is very basic, you wouldn't be thinking in alkaline. You wouldn't be thinking in terms of acidity. And so they try to avoid using the word basic for that reason. Because the word basic means not complex. They use the word alkaline to describe something that's basic. But this is correct to use. It's just, you have to know context in order to understand meaning. Whereas alkaline, you should know 100% that it's related to acids. Again, the alkaline earth metals and alkali metals all form bases. So this is an alkali metal. And then magnesium is an alkaline earth metal. These are all bases. So usually our alkaline metals and alkali metals and alkaline earth metals form bases. That's the reason why this is used. Now let's look at something complex. Let me look up so we can actually do this. 5% vinegar molarity. So 5% vinegar is the same thing as 0.833 molar acetic acid. Acetic acid is a weak acid. So acetic acid is not going to turn into H plus ions 100%. Some percentage of, so when we first put, let me just write the full one. When you put acetic acid into water, initially they're all acetic acid molecules. Over time, some of them are going to break apart into ions. So over time, some of them is going to do. Some of them are going to recombine back into acetic acid molecules. So some of the time, this will break apart into ions, and some of the time they're going to recombine together into molecules. There's a point in which it reaches an equilibrium. There's a point in time in which case we have a constant amount of molecules breaking apart and a constant amount of molecules coming back, and it stays around a certain concentration level. So I'm going to make up a number. I'll just use the word percent. X percent. There we go. So there, after a while, so initially we have 100% acetic acid and 0% H plus ions. Eventually, this will go down to like 95%, and then we'd have 5% of these. Again, every time 5% does, we get one of each. So these numbers don't add up. We get one to, it's 1-to-1 ratio. So it's going, so 95% molecules. I should probably not use percentage here. Let me just say 100. And then 95 molecules. So initially we have 100 molecules of this, then we have 0 and 0. 5 molecules are going to break apart into making 5 H plus ions and 5 acetate ions. And at some point, it's going to reach equilibrium. We're going to get a constant amount of these molecules and a constant amount of ions. And again, our pH is defined as how concentrated the H plus ions are. Every single chemical this is constant. It doesn't matter on molarity. The point in which it reaches equilibrium is a constant. It's called the K constant, and we put A beside it to reference acid. So this A means acid. And in the formula, HA goes to H plus and A negative. This constant is equal to the concentration of H plus times the concentration of H negative. And I kind of worded it does depend on concentration, but I think this constant is written in such a way it doesn't. So if you take the concentration of H plus times the concentration of A negative and divide it by the concentration of your original molecule, it's a constant. This value never changes. So regardless of whether or not I had 5% or 25% or 100% vinegar, this concentration stays, or this Ka stays constant. So vinegar Ka, and you'd have to look this up on a table. And this Ka is called the acid dissociation constant. For vinegar, or acetic acid, it is 1.7 times 10 to the negative 5. There is no units on it. There is also a KB, which is the exact same thing. This is just the base dissociation constant. Acid and bases are going to be the same thing. We just swap all H pluses with OHs. Instead of a pH, we get a POH. And its formula would be concentration of B plus times concentration of OH negative times concentration of BOH, where the formula is BOH good. So let's go back. We have tidy up. we have 0.833 molar acetic acid. Our equation is CH3COOH. And yeah, acetic acid is written weirdly. They put the H on the right. Yeah. I'm going to need to leave space on the left. I'm going to write something under it. And I looked up what the Ka was. We have the equation Ka equals H plus A negative divided by HA. And for acetic acid, Ka equals 1.7 times 10 to the negative 5. So I'm going to teach the ICE method. The ICE method. I stands for initial. C stands for change. And E stands for equilibrium. So you can treat molarity as number of moles. You can, again, because I'm not mentioning volume, pH doesn't depend on volume. So let's assume we have 1 liter. So initially, I have 0.833 mole of acetic acid. And this is right before it starts this breaking apart. I'm assuming I put all my acetic acid in the water, and it's not yet broken apart into molecules. As time moves on, it starts to break apart. Some of them are turning into H plus and CH acetate ions. Some of the acetate and H plus ions are turning back. So this is going to lose X number of moles, and this will gain X number of moles. So over time, it's going to reach some point, right, where some fraction of this will be converted into this. So it's going to lose some X number, and these two, because it's 1 and 1 right here, will gain some X. Make sense? Thus, my equilibrium is going to be 0.833 minus X. And this 0 plus X is X, and this is X. So this tells us my concentration of acetic acid once it's in equilibrium. This tells me my concentration of H plus and my concentration of acetate. So in other words, Ka, which is equal to the concentration of H plus times the concentration of A negative, which is CH3COO negative, divided by my concentration of acetic acid, it's going to reach this concentration level. So H plus is X, CH3COO negative is X, and my final result is 0.833 minus X. And this is equal to some constant. Now it's just to solve for X. And I'm going to do this in 2 different ways. So I have Ka is equal to x squared divided by 0.833 minus x. Solving for this algebraically, Ka times 0.833 minus x is equal to x squared. Distributing the Ka times 0.833 minus Ka times x is equal to x squared. Moving everything over to the right-hand side. So this will become positive on the right-hand side. That would become negative. And my Ka is this value up here. I'll go ahead and put it in. That'd be x squared plus 1.7 times 10 to the negative 5 times x minus 1.7 times 10 to the negative 5 times 0.833. Then simplifying that, do you know how to solve a quadratic formula? Do you? So if you have an expression 0 is equal to a x squared plus b x squared plus c, then x is equal to minus b plus or minus the square root of b squared minus 4ac divided by 2a. This is the quadratic formula. So in this case, my a is 1. My b is equal to Ka, which was equal to 1.7 times 10 to the negative 5. And my c was equal to Ka times my molarity, which was equal to negative, or be equal to negative 1.4161 times 10 to the negative 5. So all I need to do is plug these three values into this one. And I'll tell you right now, you're going to get two answers. Ignore the negative one. Always take the positive one. So my calculator can solve this. For brevity, I'm just going to plug in the number and solve it. Make my calculator solve this. So I get the positive answer is x is equal to 0.0037546. Now there is a trick. This doesn't work always. So you have to be very, very careful. If you want a rough estimate, so we ended up with Ka equal to x squared divided by 0.833 minus x. And we know Ka is equal to 1.7 times 10 to the negative 5. That must be equal to x squared divided by 0.833 minus x. What is this number? It's extremely tiny, right? It's a very small number. How do you get a very small number? You must have a very small bottom, or numerator, divided by a very big denominator. That means x squared, or x, has to be super tiny. Now what happens if you take a big number and minus a very, very tiny small number to it? So 10 minus 0.001. That's approximately 10, right? So what is this bottom number going to be equal to? It's approximately going to be equal to 0.833. Thus, we can solve for the approximately x squared. X squared is thus approximately equal to 1.7 times 10 to the negative 5 times 0.833, and x is approximately equal to, thus, the square root of that. So x is approximately equal to, I wonder how far off we get. .0.00376.311. So where am I off? I'm off at the 5's place. 5 and 6. So I'm going to choose to do the full algebra expression and use this value. So what do we have? We have CH3COOH, acetic acid, will partially dissociate into H plus and CH3COO negative. We're going to start out with 0.833 and 0 and 0, and eventually we're going to end up with the 0 is going to turn into with our x, or 0 turns into our x. So we're going to end up with 0.00376.311 H plus ions. So we now know our concentration, pH, is equal to negative log base 10 of the concentration of H plus ions. Well, that's how many ions we produced. So it's the negative log of base 10 of 0.00376.311. Actually, I said I was going to use the more precise number. 7.5462. So negative log base 10 of 0.00376.311. And I get a pH of 2.425434. So approximately 2.4 pH. And note that if I use the approximate number, it was still rounded to two significant digits of 2.4. Note, you can only use this if you recognize that this number is very, very small. Because if this number is very, very small, that means x is going to be very small. And thus, 1 minus a super, this is approximately 1. 1 minus a super small number doesn't really change much. This is approximately the same thing. You would get approximately the same number here. You'd only be off on the third digit. But to be honest, there's some advanced things going on, and I only really care about pH's. The 2 significant digits are to the 10th place. If you write it to the 10th place, I'm happy with it, because there's advanced things going on that make this number slightly off. So on the scale of acidity, it'd be over here at 2.4. So it's acidic. So is not as strong. I really wanted to do one more example, but I literally got 1 minute. So let's do it super fast. I'll do it tomorrow, but I just want to go ahead. Sulfuric acid. Sulfuric acid is a super strong acid. However, this should be one arrow. It turns into H plus and HSO4. This right here is a weak acid. So HSO4 negative will partially dissociate into H plus and SO4 negative 2. And I was going to do this example, because sulfuric acid is very common, but you'll see because of this, it's going to have extremely low pH.